The first talk is from Ankit and Andy on multiple control Toffoli circuit classification and transformation. So welcome, we can start.
Thank you, Aritra. So good evening, everyone. Today, my colleague Handy and I will be presenting on the topic of multiple control Toffoli circuit classification and transformation. And this work is an extension of the project which we started at QWorld 2022. So the talk is structured as follows. I'll first talk about the introduction and motivation for this work. Next, I will talk about the state of the MCT decompositions currently. Next, Henry will talk to you about the classification of permutation gates, and then he will present the verification scheme. Finally, I'll talk about the transformation between the classes and then conclude. So let's begin. Now, we all know that quantum computation has numerous potential applications from machine learning and optimization to chemistry and materials research. So there are various algorithms in literature which tackle a wide range of problems. And many of these algorithms utilize an oracle as a vital part. So sometimes the complexity of the algorithm is computed in terms of the oracle calls. This only tells us how important oracles are in a quantum computing system. Now, many times these oracles include permutation gates as a subroutine. So what are permutation gates? Permutation matrices are those which have a single one in each row and column. And MCT gates are a kind of a permutation gate. So MCT here stands for a multiple control Toffoli, which is an extension of the C0. So we know that a C0 has one control and one target. A Toffoli has two controls and one target. So an MCT has multiple controls and a single target. As an example, here you can see an oracle, an example of a Grover oracle which contains an MCT. So it has four controls and a single target. So extended from these points, we will be looking at the classification, verification, and the transformation of unitaries, focusing on auxiliary qubits. Now, what these terms mean will become clear as the talk progresses. One might ask then the motivation for this work. So we know that multi-qubit operations are hard. And by hard, I mean that there are no gates that can be acted upon by more than 2 qubits, which are available in common hardware. And the error rate for even the 2-qubit gates is higher than that of the single qubit gate. This makes it necessary to decompose the gate into constituent smaller gates. And in the NISQ era, it becomes important to consider the depth versus the auxiliary qubit count for these decompositions, as the resource availability is less and the error rate is high. Now, moving on to the MCT, we know that MCT is a common and invaluable gate, which is used almost everywhere. As such, several decompositions are available in literature. This brings us to our goal, that is to contribute to shorter and more noise-robust quantum circuits. So in this slide, I will talk about the various ways people have tried to work with MCTs. In literature, we found that different teams have focused on minimizing different resources, so such that the depth of the circuit, and not just the total depth of the circuit, but depth of a single gate, like the T gate, which is sometimes called the T depth. People also want to minimize the total number of C0 gates that are in the decomposition, or the total number of T gates that are in the decomposition. Another resource that is important is the number of qubits that are being used. As such, people want to reduce the total number of auxiliary qubits. But this is not all. These decompositions are comprised of different basis gates. Now, here we have shown some of the basis sets that we found in literature. First one is the Toffoli. This means that you will find papers where they will decompose the multi-control Toffoli gate into Toffoli gates, but not go any further. Sometimes you'll find that they will go further and decompose it into Clifford plus T set, or the Clifford plus Zn set, where Zn is the nth root of Z. There are other basis sets like the NCV, NCVW, or the NCR, where each of them is a sum root of the NOT gate. So this just shows us the variability in the decompositions that are present. But even the story doesn't end here. Sometimes you'll find that the MCT that you are making is absolute. And sometimes you'll find that it will leave a face on the target cube. As such, we are left with a view that there is a high variability in MCT decompositions, and this further motivates us towards making a general classification scheme. Now, Hendy will take you over to the next part.
All right, thank you, Ankit, for the introduction. Now, the question is, how do we classify the MCT permutation? It is easy. We just need to start with the question ourselves, like, is the circuit it comes with an auxiliary qubits or not? Then if it's not come with the auxiliary qubit, we can classify them as a no auxiliary. And if it comes with an auxiliary qubits, then we need to start another question whether the input state of this auxiliary qubit, it starts from cat 0 or not. If it starts from cat 0, then it can be considered as dirty. And then another question is whether the output state for the auxiliary qubit is the same as the input or not. If it's the same, then we will classify this as dirty, non-wasted auxiliary. And if it's not, then we will also have another questions to whether the output state is entangled or not. If it's entangled, if it's not entangled, then it will go to the dirty, wasted auxiliary, separable left out, and if it's entangled, then it becomes dirty, wasted, auxiliary, entangled. And now with the other side is if it's the input state, we started with the cat 0, then it means it's clean is the same as the other side, like it will become clean, wasted, non-wasted auxiliary and the other stuff. All right, and now as we can see that we have classified them into 4 states, 4 classes. The first one, we classified them based on the input state of the auxiliary qubit, and we divide them into clean and dirty. And the second one is based on the output of the state of the auxiliary qubit. We divide into non-wasted and wasted here. And now we also add some 4 phases. Is we divide into strict and relative phase here. And I will explain all of this later. And the last one is wasted auxiliary. It's entangled or separable. In the case of the input state, so we just need to focus on the initial value of this auxiliary qubit. As you can see, for clean, it started with cat 0. And for dirty case, it can be arbitrarily started with any value. So like for the example, it's like 101. And we are using these circuits from the paper of Barenko et al., Elementary Gates for Quantum Computation. And now this is the second category that based on the output state. Now we can see here like for non-wasted, it starts with 101 and it's end up with the 101 again. So to be non-wasted, it means that the status of the value of quantum auxiliary qubit should be the same from initial and the output after the implementation of the MCT. And we can see for the wasted, it's changing from 101 to 010. That's why it becomes wasted. And the third one we have based on phase. And here is this circuit is, as you can see, it's Toffoli gate, and the second one is RCCX. It's only differ by the phase. As you can see, it's only like this matrix, it's all one, but the second one for the RCCX, it has like differences by the phase, but it works the same. And the last classes, we have this entangled and separable. For this entangled, it means that the final state of the auxiliary qubit will become entangled with the control and the other, like for the control qubits, but it's not always happens. So it only happens when the input state of the control is like a Bell state where it's like entangled. And for the separable, it's basically the same, But since we only need to remove all the last two gates that directly affected the auxiliary qubits, and it will become wasted, but it's separable qubits with the other qubits. And now this is all the list of MCT that we have classified. So like in total, we have around like 14, and we are focused more with the classification of with the auxiliary qubits here. And now here we add these three. So for each of this class, for example, DWRE is like a set of unitary matrix. So okay, it's a classification for the permutation that we have. And for the error is like we have the inclusion for this one, and so it's like inclusion for the dirty one. So in this case, it's like dirty is a special case of this clean. So we only have to add some parts of the gates and it will become dirty from clean. And then, oops, sorry. And here we have strict MCT is like a special case of relative phase. So we can see like this. And then non-wasted is a special case of wasted. So everything will become like connected. And separable is special case of entangled. Now, to make sure, okay, so first I will explain what is this U tilde. U tilde is a unitary matrix from our verification. So and U is a unitary matrix for MCT implementation. So this you don't have to understand about this mathematics, but if you want to know better, then we will have our paper ready next time, so you can check our paper. And then this is what we do, make sure that the MCT implementation that we are using is also producing the same unitary matrix that for the same verification. And here we choose some implementations from popular literature, and some of them is like Barenko and Qiskit. So we choose the best one, and then from here we check whether the implementation from this is like from our verification. For example, if it's for this example phi chain dirty, you can see here like if it start from here, then it's also like it's like the inclusion of this and this and from at the top, so everything is like will be concluded like it will pass off the verification. So from all this verification, we also on progress in making a software where we will provide the software in Python to user if people want to apply any MCT like MCT implementation based on their requirements. For example, they want to have the minimized number of depth and the minimized number of CNOT. So we will like, they just call our function and we will provide the circuit for the most efficient circuit. And now my friend Ankit will continue with transformations.
Thank you, Henry. So all of you now know about the classifications and the verifications. So now I look at the transformations. So individual users will have unique requirements. So they will want to have some class, as Henry mentioned, that you might want to reduce the number of T gate or the C0 gate, and we'll want to provide that. So it will be better if the user can choose and can go from one class to another. And if by doing so, they will reduce the resources that are being required. And so how this whole works, I will show you by using an example. So we will take a look at this MCT circuit, which is part of type is the dirty non-wasted auxiliary. So let's see what happens. Now, if you focus on these gates, you note that these are controlled by the input auxiliary state. So if A0, A1, A2, A3, the auxiliary qubits, if they start with zeros, you will know that these gates will not apply. So as such, we can remove them. And once we remove them, you will find that the depth has reduced and now the auxiliary starts from zero. So this transformed circuit is part of a clean, non-wasted auxiliary. Now you can do something similar. So we have this original circuit and we will look at these gates. Now you note that these gates are acting only on the output of the auxiliary qubits. So whatever is happening here does not have any effect on the target. So we can remove these gates also. And once we remove these, we are left with the dirty wasted auxiliary. Because now the auxiliary qubits are not in the same state as they were before, but the target has not changed. It is still acting as an MCT, but it is a dirty wasted auxiliary. Which brings us to our next point. From the original circuit again, we first removed these, supposing that we are starting with clean auxiliaries, and we remove these, supposing that these are only acting on the output auxiliaries. So if we can combine these two, we will find that our MCT is now much shorter and is a part of the clean wasted auxiliary, because now we are starting from the clean auxiliary qubits and we are wasting them. So you see that depending on your usage, the qubit requirement, the depth requirement, the gate requirements can reduce. And this is what we want in the NISQ era. So in conclusion, we have created an extensive classification scheme and provided mathematical backing for the same. And we have made verification functions that can take your circuit and tell you which class it belongs to. And we have implemented various MCT decompositions and also implemented the transformation between the classes. Now, this is still a work in progress, and we'll hope to cover many more classes and many more decompositions. Thank you. We'll be happy to take any questions now.
Thank you, Ankit and Handy. So this looks like a very small problem, but this is like actually very useful for algorithms like Groover search, where there's lots of Toffolis involved, like multi-control Toffolis. So also, I had one small question, like, so for some algorithms, for example, when you are iterating over the repeated Groover search, in the repetition, it matters how much phase you're adding. So if your Toffoli decomposition has this phase, how do you deal with it? Like if you don't have, let's say, added ancillars and the Toffoli decomposition that you chose has a phase, is there a way to get around that problem?
Yes, so what we can do is we can switch. So if you have an absolute Toffoli, you can remove some gates and change some gates to go to the relative Toffoli. So the relative Toffoli always uses less gates. So resource requirement is less. But if you know that the phase is going to matter, you can add those things back. So those gates you can add back and go to the absolute. So the whole point of this is whatever the user requires, whatever your requirement is, we will tailor our MCT to that. So if you know that, okay, my qubits are going to be clean, but I want the phase to be correct, and we will give you a clean MCT which is absolute and will not use the relative ones.
Okay, yeah, thank you. There's one more question from Shashi. Can you also take into account the connectivity constraints when you are decomposing it?
So this is a good question. So this is in our radar, but we have not implemented this yet.
Okay, yeah. And there's another comment from Maya that once you have the paper, it'll be really good if you can share with the community. We'll be looking forward to that.
Yeah, as Handy has said, that it is work in progress, and we will be happy to share it. Thank you all.
Yeah. Thank you. Thank you once again.